In this video, we're going to talk about something called the first isomorphism theorem. So to set the stage, suppose I have a ring. Suppose R is a ring. And I is an ideal of R. And I want to analyze the structure, or just understand the structure of the quotient ring R mod I. The first isomorphism theorem gives me a nice and straightforward way to understand this structure if I can realize this ideal as the kernel of a homomorphism from R to some other ring. So here's the theorem. Assume R and S are rings, and let's assume that phi from R to S is a homomorphism, not necessarily an isomorphism, just a homomorphism. So it preserves addition, preserves multiplication. Then the quotient ring R mod K, where K is the kernel of phi, is isomorphic to the image of phi. And just as a reminder, the image of phi is the set of all elements y of S such that y is equal to phi of x for some x in the domain. Okay, so in other words, the image of that function. All right, so R mod the kernel of the map is isomorphic to the image of the map. That's kind of a nice, elegant theorem, wouldn't you say? So here's the proof. First of all, note that K is an ideal of R by one of our theorems from a previous video about homomorphisms. This is something that we checked. If we have a ring homomorphism, its kernel is an ideal of R. And the reason I'm taking care to point that out first, even before getting into showing that R mod K is isomorphic to anything, is that for us to be able to even talk about R mod K, we need K to be an ideal of R. So this establishes that. Okay, so now we're going to build an isomorphism, which I'll call C, from R mod K to the image of phi. But before we define that map, I want to talk a little bit about the intuition of the isomorphism here and how we think about the quotient ring R mod K. So here's a picture. I'm going to draw a little cartoon of a ring. All right, so this represents R, and the smaller box will represent S. Now let's imagine I have a bunch of points in R. Each of these points represents some element of R. You get the idea probably. And then all of these points map to something in S, or more specifically, each point in R maps to some point in S. And maybe that map looks a little bit like this point goes to this point in S, and then this point goes to this point, and this point goes to this point, and so on. Each point in R has some image in S. I'm just drawing a few representatives to help set the stage here. Okay, now the idea of the first isomorphism theorem is that if the kernel of this map phi is non-trivial, then elements of R are going to go over into S in chunks. So for example, if the kernel is non-trivial, then I can develop the cosets of the kernel, the cosets of K, which might look like this. So I might have a couple of cosets here, and then a couple of cosets here, and then a couple here, and then maybe a couple here. And actually the cosets, so one thing that's deceptive about this picture is that each coset should have the same number of elements. The picture is kind of not faithful in that regard, let's just put it that way. Okay, so we should think of each coset as being about the same size, and that looks a little bit better anyway. But if this coset, for example, is K, or 0 plus K, then we know that all of the elements in that coset are going to go to the same element of S. That element's going to be 0. And then maybe I have some other coset here. This coset is A plus K. That coset, every element in there is going to go to the same element of S. That element is going to be phi of A. And then if this is some other coset, B plus K, then each element in that coset is going to go to phi of B, and so on. Each coset has its own destination, but that destination is shared among all of the elements of the same coset. And that's because if I take some element like C here, well, C I know is going to go to phi of C, but every other element in this coset is C plus some element of the kernel. So if I map through, I'm going to get phi of C plus phi of something in the kernel, and that phi of something in the kernel is 0. All right, so anyway, the way that we're going to build this map is each coset is going to go to one element of S. And notice that not all of the elements of S have to get hit. I may have some other points over here that are not even outputs of phi. Those are going to get ignored when I develop this map. Okay, so here's the definition. Define C from R mod K to the image of phi by C of A plus K equals phi of A for all A in my ring. All right, so in other words, if I want to know what C does to some coset in R mod K, remember R mod K consists of cosets of the kernel, then I take that coset, I look at some representative, call it A, and then I map this coset here, to whatever phi mapped this individual element to. In terms of the picture, I could think of it this way. If I want to know what element of S this coset is going to go to, let's take this coset right here, and let's call that D plus K. Then I take some representative of that coset, we'll call that D, and I see where D goes under phi. So phi has to map this somewhere, maybe it maps it right here. If that's the case, then I'm going to take this entire coset, D plus K, and C is going to map that coset to the exact same element. So this is phi of D, but by our definition, it is now also going to be C of the coset D plus K. So that's how we construct the map. Now there's an issue here, which is that we're not done with the proof. We have to show that what we have here really is an isomorphism. And that begins with showing that not only do we have a homomorphism, we have a well-defined map. We need to show that, first of all, this map is well-defined. A bit more on that in just a minute. Once we've done that, we will need to show it's a homomorphism. In other words, preserves addition and multiplication. Then we need to show that this map is one-to-one. And finally show it is onto the image of phi. All right, the sticky part is really this first one. The rest, there's certainly some work to do with them. There's certainly some work we'll need to do to show that this is a homomorphism, some work to do to show it's one-to-one, and a little bit of work in showing it's onto. But most of the work of understanding the proof of this theorem is right here, proving that C is well-defined. All right, I'm going to zoom this out while keeping the picture in frame so we can do a little bit more work here. But what do I mean by well-defined, and why is that an issue here? Well, the problem is, if the kernel is non-trivial, a coset of the kernel is going to have a lot of different names. So for example, looking at my picture, when I was talking about D plus K earlier, I named that coset using this element here, D. But maybe someone else would look and focus on this element here. Maybe they'd call that, I don't know, some other random letter like P. And then to them, this coset is not D plus K, it is P plus K. So we need to have some way of showing that whatever element from this coset we pick, we're going to end up mapping this coset to the same element, which is this one right here. All right, so what we need to show, we need to suppose that A and A prime are elements of R such that A plus K equals A prime plus K. And we need to prove that phi of A is equal to phi of A prime. Because once we've done that, then we'll know that C of A plus K is equal to C of A prime plus K, which means these two equal cosets end up giving us the same answer when we map them through our function. All right, so to prove this, well, we've assumed that A plus K is equal to A prime plus K. So that means, since A plus K is equal to A prime plus K, because of all the work that we did with congruence classes, we can say this is equivalent to saying that A is congruent to A prime modulo the ideal k. So there is some element, I'm going to call it lowercase k, belonging to the kernel, such that a plus k is equal to a prime. All right, so what does that mean? So then phi of a prime, that's equal to phi of a plus lowercase k. And because phi preserves addition, that's phi of a plus phi of k. And because k belongs to the kernel, that last bit there, phi of k, is 0. So that means we have phi of a, which means these two are equal. That's exactly what we wanted. So because phi of a equals phi of a prime, we can say psi of a plus k is equal to psi of a prime plus k. And that's something that is absolutely crucial because these are the same coset here. If psi doesn't map into the same thing, we don't even have a function here. So now that we've proven that, we know psi is well defined. That's the first step right there. And the rest is going to be smoother sailing, I think. So I'm going to move away from this picture. Hope that we can figure out the rest just by following these steps here. Okay, step 2. To show this is a homomorphism, suppose a plus k and b plus k are elements of R mod k. Okay, so anytime I want to show a map's a homomorphism, I need to take two random arbitrary inputs and prove that my map preserves addition of those and preserves multiplication of those. And in this case, the inputs are from R mod k. That means they've got to be cosets. All right, so then we have, what is psi of a plus k plus b plus k? Well, by definition of coset addition, that's psi of a plus b plus k. And by definition of psi, that's phi of a plus b. And well, I know that phi is a homomorphism, so phi preserves addition. That's phi of a plus phi of b. And again, by my definition of psi, that's the same as psi of a plus k plus psi of b plus k. Okay, so that shows that psi preserves addition. I'm going to leave off the proof that it preserves multiplication because it's exactly the same thing, just exchange all the addition signs for multiplication signs. Other than that, it's pretty much the same proof. The only thing you have to be attentive to is here, we're going to be multiplying two cosets. Well, how do we multiply a plus k times b plus k? That by definition is just ab plus k. And then after that, the proof works out exactly the same way. All right, let's talk about why psi is 1 to 1. All right, so to show that this map is 1 to 1, we're going to use a strategy from our first semester abstract algebra course, and that is to show that a homomorphism is 1 to 1, we only need to prove the kernel is trivial. So we'll show the kernel of this map, so not k, but the kernel of psi, is trivial in R mod k. All right, so suppose a plus k belongs to the kernel of this map. Remember, the kernel consists of inputs from our domain of the map, which is R mod k. All right, well then that means psi of a plus k is equal to the 0 element of S. But then by my definition of psi, that also means that phi of a is equal to 0 of S. All right, so, well, what does that mean? That means that a belongs to the kernel of phi, which is exactly the thing that we were calling k. And that means that the coset a plus k, that's really just k. That's the 0 element of our quotient ring. The 0 element of our quotient ring is always the ideal itself. Okay, so this means so the only element of the kernel of psi is k itself. That's the additive identity of R mod k. So the kernel of this map is trivial. Thus, the map is 1-to-1. And then the last step is to prove that this map is surjective. But remember, we only need to prove it's surjective onto the image of phi, not onto S. It won't be surjective onto S necessarily. So to show that this maps onto the image of phi, well, first a little bit of intuition here. We should expect this, I think. And here's why. Looking back at my diagram here, sorry, I know this is kind of dizzying here. Well, if something is in the image of phi, that means there's somebody that maps to it. So let's imagine all of these points on the left. These are the ones that phi actually maps to. Okay, so if I take some point that phi maps to, there is somebody over here specifically who maps to it, but then that means the entire coset of that element maps to it. And that's how we're going to show that psi is onto. We're going to say, well, if something's in the image of phi, then there's an element of R that maps to it, but that means there's also an element of R mod K that maps to it. It's the coset of that element of R. So that's how the proof is going to work. Let's write it down. Okay, zoom out. Come on. There we go. Sometimes this thing is a little bit stubborn. Okay. All right, so to prove that psi maps onto the image of phi, here's how we do it. Suppose Y belongs to the image of phi. Then there is some X in R such that phi of X equals Y. But then, by definition, psi of X plus K is also Y. And that's pretty much the proof. So Y belongs to the image of psi. So the image of psi is equal to the image of phi. Okay, there is one thing I'm being a little bit sloppy about. I think technically what I showed here is that the image of phi is a subset of the image of psi, not the other way around. Okay, so why is it the image of psi has to be contained in the image of phi? Saying these letters, by the way, gets to be a real chore after a while. But anyway, why is it that psi can only map to things in the image of phi? Well, remember, we defined psi of anything to be phi of that coset representative. So if I take psi of any coset, what I'm going to get is always going to be in the image of phi for that reason, because it's always phi of something. So that's why these are equal and not just this is a subset of this. And that's it. That is the entire proof of the first isomorphism theorem. And everything here is so abstract. I mean, I know this is abstract algebra, but this is like beyond abstract. Everything here was pretty much devoid of specific rings, specific ring elements. The only thing approaching an example is this picture here. So you might wonder, what could we do that's really powerful with a theorem that is so general in its reasoning? Well, we'll find out in the next video.